Hello, my name is Shahriari, and this is a lecture in a series of lectures on introductory combinatorics based on my book, An Invitation to Combinatorics. The subject of this lecture is the proof of Ramsey's theorem for two colors. That's basically all we're going to do. To get started, let me remind you what Ramsey's theorem is about. I had a previous video where I discussed this in some detail, and I urge you to watch that before watching this video. This video proves the theorem. The previous video explains what it means and the notation. So it's important to sort of understand that notation before, even though I'm going to remind you of that right now. So the idea is that we start with S, a positive integer, and we look at the complete graph of order S. So this is S vertices, and every two vertices are connected by an edge. There's no double edges, and there are no loops. That's the complete graph of order S. Then what we do is we color the edges of this complete graph. And for now, for this lecture, with two colors, blue or red. And this is arbitrary coloring. So somebody else might do this for you. And then you're going to ask a question. Are you guaranteed that within that KS, you will have a blue KN? KN is the complete graph on n vertices, and n is going to be smaller than S. And a blue KN means that a KN where all the edges are blue. Can you find n of the S vertices such that every edge between those vertices in that collection of n vertices, all of them are blue? Well, you might not be able to do that for sure, because it might be that the coloring was all red and there's nothing blue, and therefore you can't guarantee a blue KN. But you're going to give yourself a little bit of flexibility and say, what about if I can I guarantee a blue KN or a red KM? M, another integer smaller than S, and a red KM would mean a complete graph on m vertices where all the edges between those vertices are colored red. If someone gives you a coloring of KS, and by that we mean coloring of the edges with two colors, can you guarantee a blue KN and a red KM? And the answer is most likely not. However, sometimes you can, depending on what S is and what N and M are. And we write this thing in this arrow notation. The arrow notation is written KS arrows, KN or KM. And all that means is that this is a claim. Again, a claim that may or may not be true. This claim might be false, might be true. Again, if you just sort of randomly write a claim like this, most likely it'll be false. What the claim is if you arbitrarily color the edges of a KS using two colors, blue and red, then you are guaranteed a blue KN or a red KM, or both. Mathematics or is always inclusive. And so when we say or this or that, we are allowing for the possibility of both happening. Okay, so this is a claim. And again, most of the time, it's going to be false. Now, what Ramsey's theorem says is that if you start with your wish list, with n and m positive integers that are going to be your wish list, what you're going to look for. You're going to be looking for a blue KN or a red KM. And then there will be a positive integer S, which will depend on n and m and probably will be large compared to n and m. So such that KS arrows to KN or KM. So the idea is that if you pick S large enough, then yes, you will be able to guarantee a blue KN or a red KM, as long as you fix N and M. You fix N and M, maybe N is 15 and M is 27, then Ramsey's theorem will say that yes, if you pick S large enough and then go and color the edges of a complete graph KS with two colors, then you are guaranteed that within that coloring, you will be able to find a blue KN or a red KM. Now, this is quite surprising. I mean, amazing. Like, why is that? Why is it that you can guarantee that no matter how large S is? Even if large S is large, you might think that you might be able to do the coloring in some way to avoid a blue KN and avoid a red KM. And Ramsey's theorem says that's not the case. In other words, if the system is big enough, if your complete graph is big enough, then you're guaranteed this order within that chaos, the chaos being the arbitrary coloring of the edges. You are guaranteed a blue KN or red KM, no matter what the coloring is. because of Ramsey's theorem, we can define Ramsey numbers. So again, n and m positive integers, those are our wish list. I want a blue kn or a red km. And I know by Ramsey's theorem, there is some s such that if I look at ks, then that ks arrows to kn or km. But the smallest such positive integer for which ks arrows to kn comma or km is called the Ramsey number RNM. Okay, and we have now in our previous video we talked about this. We have some obvious things about these Ramsey numbers. For one thing, they're symmetric. There's no really difference between red and blue. So RMN is the same as RNM. If I'm looking for a blue KM and or a red KN, the smallest s that I need is going to be the same thing as the one that will give me guarantee me a blue KN or a red KM. If I have R1M or RM1, what are those? Those are just going to be one, because if you have just one vertex, there's no edges, and you will be guaranteed a blue K1, because a blue K1 is just a vertex and it doesn't have any edges. So all of its edges are already blue. So you're good. And R2M, RM2, what does that mean? R2M means that I'm looking for blue K2 or a red KM. And the answer to that is going to be M, because if you start with a KM, either you will color some edge blue, in which case you have a blue K2, or you won't and use only red, in which case the whole thing will be red and the whole thing would be a red KM. So these are some ones we know. We also, this is for M greater than 1, because if M is 1, then the previous line will take precedence and R21 will be 1. We also proved that R33 is 6. So if you have a K6 and color the edges with 2 colors, then you're guaranteed a monochromatic triangle, a blue K3 or a red K3. And we went through the proof of this in the previous lecture. It's a very nice proof. You definitely should see it if you have not. However, we have to actually establish that this RNM actually exists. I mean, just saying that this is called the Ramsey number doesn't mean that there is such a Ramsey number. Ramsey's theorem says there is such a thing. There is such some s, and if there is some s, then there's the smallest one, so that works. But we really have to prove that RNM exists, and that's what we are going to do. Now, as a warm-up, I'm going to try to prove that R34 is less than or equal to 10, and then the proof will show you how the more general proof will go. In fact, what we'll be showing is that R34 is less than or equal to R24 plus R33. That R24 is 4, R33 is 6, 4 plus 6 is 10. That's where that 10 comes from. R34 is actually 9, but that will take a little bit more clever argument to get the 9. But I'm not interested in finding the smallest, the actual value for R. There's no formula for RNM. But what I'm interested in showing is that RNM actually exists. And so what I want to show you is that I want to show you from the known ones that we already know how we can establish that a bigger one, R34, exists. There is some number that works. And in particular, I'm going to prove that it's less than or equal to 10. So again, we know that R24 is 4 and R33 is 6. And we want to show that R34 is less than or equal to 10. And actually, what we will be showing is that R34 is less than or equal to R24 plus R33. We're going to be bootstrapping what we know R24 and R33, to show that some R34 is less than or equal to their sum. In particular, R34 will be a finite number and exists, as Ramsey's theorem predicted. So this is our way of showing that it exists, by showing that there's a finite number that will work. So how do we show that R34 is less than or equal to 10? Well, what we have to show you is that K10 arrows to K3 or K4. So what that means is that if I have a K10, here's my K10, and if I use blue for my first color and second color red, and I color all the edges blue or red, I haven't done that, but if you do that, it would be quite messy. There's a lot of edges there. If you color all of them in some fashion blue or red, then you're guaranteed a blue K3 somewhere, somewhere there will be 3 vertices such that all of their edges will be blue, or you will get a red K4 somewhere. So 4 vertices such that every pair of vertices is connected by a red edge, or both. You might have both of them, or you might have 2 red K4s, but at least there will be a blue K3 or a red K4. So the way we're going to do that is we're going to focus on one vertex, V, of the 10 vertices. We're going to vertex V. That vertex has degree 9. What does degree mean? The number of edges incident with it. There are 9 edges that come out of V. One for every other. There are 10 vertices altogether, and there's an edge from V to every other one of those. So the degree of V is 9. Now, here's something I'm going to say. There's 9 edges coming out of V, and you're going to color them using blue and red. So what can happen? Well, you could make all of them blue. You could make all of them red. You could try to be even, and well, it can't be quite even, but you could have 5 of one, 4 of the other. But what I'm going to say is that among those 9 edges, there's going to be at least 4 blue edges. Well, I can't promise you that, or at least 6 red edges. So either there will be 4 blue edges or more, maybe 5 blue edges, maybe 6 blue edges, but at least 4 blue edges, or at least 6 red edges. Again, maybe more. How can I guarantee that? So let's think about the argument. The argument is proof by contradiction. What if that was not true? What if there wasn't, there were fewer than 6 red edges and fewer than 4 blue edges? Well, if there were fewer than 4 blue edges, then there would be at most 3 blue edges. And if there were fewer than 6 red edges, then there would be at most 5 red edges. And 3 and 5 is 8. But we've got 9 edges here, so that can't be. So you can't have at most 3 blue edges and at most 5 red edges, because that would be 8. But we have 9. So that means that at least I'm going to have 4 blue edges, or at least 6 red edges. I can't actually have both, because there's only 9 edges coming out. So I can't have 4 blue edges and 6 red edges, but I'm saying that at least 4 blue edges or at least 6 red edges. This was sort of a pigeonhole principle argument. So I'm going to have 2 cases, the case where I have 4 blue edges and the case where I have 6 red edges, and I'm going to argue about those. So case 1 is I have at least 4 blue edges. That's the one I'm going to do right now. And in the next slide, I'll do the other case where I have at least 6 red edges. So I want to show that K10 arrows to K3 or K4. And we have colored each edge of K10 with blue or red. And we want to show there exists a blue K3 or a red K4. And what I do know here is that we have focused on one of the vertices, and the case we're considering is when there are 4 blue edges incident with V. 4 blue edges, 4 or more, at least 4 blue edges. So take 4 of, if there are more blue edges, don't worry about the other ones. Just look at 4 blue edges. And what I'm going to do is I'm going to consider the other ends of those blue edges. So the other ends are vertices. So there are those 4 vertices that are the other ends of those blue edges. I don't know which ones are the blue edges, but I know that they have some other vertex at the other end of them. So look at those. Now, this is what I'm going to say. I'm going to say either there's a blue edge among them, like they're connected with a blue edge, maybe this one, maybe that one, maybe that one. And regardless of which blue edge there is, that blue edge together with the 2 blue edges coming out of V to those 2 vertices gives me a blue K3. And a blue K3 was one of the things that I was wishing for. I was trying to show that K10 arrows to K3 or K4, a blue K3 or a red K4. A blue K3 was one of the things that I wanted. So if one of those edges is blue, then I've got myself a blue K3 and I'm good. But maybe that's not the case. Maybe none of those edges are blue. If none of those edges are blue, it must be that they're all red. But if they're all red, then that's my red K4. All those vertices are connected together with, there are 4 of them, and all of their edges are red. So that's giving me a red K4, and I'm done. Now, notice that we have actually implicitly used the fact that K4 arrows to K2 comma K4. How did I use that? Well, I had a K4 because these other ends, there were 4 vertices, and they were all their edges were connected, and those edges were colored with 2 colors, but it was a K4. And because K4 arrows to K2 or K4, blue K2 or a red K4, I knew that among those there was going to be a blue K2, which together with V then would give me the blue K3, or a red K4, which itself was good enough. So I didn't explicitly use that here. I will for the next case, but I was using this prior case, this easier case. Now let's go to the second case where we know that again we're in the same situation. We want to show that K10 arrows to blue K3 or K4. We have colored each edges of K10 blue or red, and we want to show that there exists a blue K3 or red K4. But now we are again focusing on one vertex V, and we're in case 2 where we know 6 of the edges coming out of V. We don't know which ones, but we know they're red. Again, we're going to consider the other ends of those 6 red edges. So now I've got 6 vertices here. Now 6 vertices that are all connected together, that's a K6. And what I know about K6, which I proved in the previous video, is that K6 arrows to a blue K3 or a red K3. If you take a K6 and color all the edges with blue and red, you are guaranteed a blue K3 or a red K3. Okay, now what? So what? Well, if you have a blue K3, so that's one of the possibilities, then we're good. Why we're good? Well, because a blue K3 was one of the wish lists that we had. So if among those 6 there is a blue K3, then we're good. But there might not be a blue K3. We might have a so any one of those would be good, or we might have a red K3 among them. But what about a red K3? That's not what I wanted. I don't want a red K3. I want a red K4. But see, this is when we remember that the V was connected to all of those 6 vertices by red edges. And so those 3 vertices that are connected by a red edge together with V now form a red K4. And you've got to say that this was a really nice proof. So now I've got my red K4 and I'm done with my 2 cases and I'm done. So I proved that R34 is less than or equal to 10, that K10 arrows to K3 comma K4. Actually, if you think about it a little bit more and you're a little bit more clever, you can prove that K9 arrows to K3 comma K4, but that does take a slightly different argument. You can't focus on just one vertex. You have to look at all of them. Okay, so now let's look at the general case. So N and M are so I'm just going to tell you how we're going to prove Ramsey's theorem. N and M are integers greater than 1. I'm going to assume that I've done earlier cases. I've done Rnm minus 1m and Rnm minus 1. So I've done those 2 cases and I know those numbers exist. So I know that there is a big enough number such that if you take a complete graph with that many vertices, it arrows to Kn minus 1 or Km. And also another one that arrows to Kn or Km minus 1. So I'm assuming those earlier cases have been done. And then then I'm going to prove to you that Rnm, the one that I want to find, is less than or equal to Rnm minus 1 comma m plus Rn comma m minus 1. This actually proves that because we already know the earliest cases, that we know, for example, that Rn1 and Rn1m is 1, using those and then using that relationship Rnm less than or equal to Rnm minus 1m plus Rnm minus 1, we can just fill up the whole table and show that all of these numbers, no matter what n and m are going to be finite numbers. So this will be our proof that how we prove that Rnm is always a finite number. We assume that we know some smaller ones, and we do know some smaller ones, and then from them, well, we get that the bigger ones are bounded. We're not finding what Rnm is, we're just finding a bound for them. We're showing that it's finite. And so a corollary of this will be Ramsey's theorem, that n and m positive integers, then there is this positive integer s such that ks arrows to kn comma km. Why? Well, because that s will be rn less, rnm will work, and that rnm is less than these previous ones. Just to make sure that we are on the same page regarding how this recursive proof is working, let's see how this would work. So this relation, actually, I'm claiming that if I can prove this, I haven't proved it yet, but if I can prove it, then this gives upper bounds for every RNM. Why? Well, because here I'm going to, in this table, I'm not going to put RNM, but I'm going to put bounds for RNM, upper bounds for one RNM. So if n is 1 through 6 and so on, and m is 1 through 6, I know that the first row and the first column are all ones. I know that was R1M and Rn1 being 1. Now, because of that and because of this relationship, I can tell you that R22 is less than or equal to R12 plus R21. That means that it's less than or equal to the sum of these two. 1 on 1 is 2. And then from that, I can get that because this is less than or equal to 2 plus 1, R23 is less than or equal to 3. Now, some of these, like for example, these two, I actually know that they're equal, but this theorem just tells me less than or equal to. And then this continues. I can complete that row. I will know that that row is all less than or equal to those numbers. Again, those are actually equal to, but the theorem doesn't tell me that. I know that from my discussion before. I can do the same thing down the column. So this R32 is going to be less than R31 plus R22. So less than 1 plus 2 is 3. Then 1 plus 3 is 4. 1 plus 4 is 5. 1 plus 5 is 6. So and then I go to R33, and R33 is going to be less than R32 plus R23. 3 plus 3 is going to give me 6. And you can then continue that row, for example, and R43 is going to be less than R33 and R42. So if you add those up, you get 10. And you can then continue like that all along that row, and then you just keep going down and filling up more rows, and you can go as far as you want. And so these will be bounds for the Ramsey numbers, all the Ramsey numbers. And this tells you that because if you have that relationship that Rnm is less than or equal to Rn minus 1m plus Rnm minus 1, and because we know the first row and the first column, then we know that there's some number that's going to work for all. So there's some bound for Rnm, so Rnm is finite, and therefore Ramsey's theorem is proved. By the way, if you know about binomial coefficients, if you know about the so-called Pascal's triangle, something that I like to call Karaji-Gia triangle, you might want to notice that this is actually the triangle on its side. And so binomial coefficients actually are giving a bound for Ramsey numbers. That's something that will be a subject of a later video after we talk about binomial coefficients in more detail. But now to the actual proof. So S is going to be R of n minus 1 comma m plus Rn comma m minus 1. This is a finite number because I'm assuming that these prior cases have already been done. I'm thinking that I'm filling out that table and I'm doing it in order. So I've done the previous cases, and I want to show you that Rnm is going to be less than or equal to S. Rnm isn't necessarily equal to S, the sum of these two numbers, but it's going to be less than or equal to S. So what does that mean? So think about that for a second. How would I show that? Stop the video. Think about, do you understand what I'm talking about so far? Or is it just sounds gibberish? But you should understand that what I'm really trying to show now is that Ks arrows to a blue Kn or a red Km. So, and again, expanding that further, that means that if you arbitrarily color the edges of a complete graph Ks, what's S? S is the sum of these two numbers. Then you should be able, using blue and red, those are the two colors. Blue is the first color, red is the second color. Then we have to show that we are guaranteed a blue KN or a red KM or both, or many more, but at least one blue KN or at least one red KM. Okay, so how am I going to do that? So again, I'm going to repeat the same thing that I did in that particular case where I showed that R34 is less than or equal to 10. I'll focus on one vertex. I'm not going to draw a graph here because our proof should not really depend on our visual looking at the graph, although that's the thing we always do. We should be able to do this without drawing a graph. So we focus on a vertex V of Ks. The degree of that vertex is S minus 1. It's connected to S minus 1 vertices, the other S minus 1 vertices of the complete graph on S vertices. And we're going to claim that, so this is the claim that I'm going to make, that among those edges, at least R of n minus 1 comma m of them are blue. Or if that's not the case, that doesn't have to be the case because maybe you colored everything with red. Or at least Rn comma m minus 1 of the edges are red. Okay, now why is that? Well, again, the proof is by contradiction. If that wasn't the case, then that would mean that at most R parentheses n minus 1 comma m parentheses closed are blue. And at most Rn comma m minus 1 are red. But if that's the case, so if there's one less blue and one less red than what I'm claiming here, then the total number of edges would be Rn minus 1 comma m plus Rn comma m minus 1 minus 2. And that's S minus 2, because S is the sum of these two numbers. But if both of them are one less, that would be S minus 2 edges. But the degree of degree of V is S minus 1. One of the edges isn't accounted for. And that's a contradiction. So if you color all the edges, you can't avoid having either this many blue edges or more, or this many red edges or more red edges. Okay, so again, we have two cases, just like the case R34 less than or equal to 10. If this didn't make sense to you, go back and review that proof again. And I'm going to do the two cases. So case one is that, so what's the case one? So I've colored edges of a complete graph on S vertices blue and red. I want a blue Kn or a red Km. I want to show you that there exists such a thing. T, I'm going to call that R of n minus 1 m. That whatever that number is, I'm assuming that number exists. Whatever it is, I'm going to call it T. And I'm in the case where T of the edges, at least T of edges incident with V are blue. That was our case one. At least R n minus 1 comma m edges incident with V are blue. I'm giving that thing a name, T. So I know that T edges coming out of V are blue. So what? Well, consider the T vertices at the other end of those blue edges. So now I've got T vertices hanging out there, all connected to V by blue edges. But what's T? T is Rn minus 1 comma m, and that's a Ramsey number. So KT arrows to a blue Kn minus 1 or a red Km. If you color all the edges of a KT with blue and red, then you're guaranteed a blue Kn minus 1 or a red Km. Why? Well, because that's what the Ramsey number tells you. And this is the Ramsey number that we assume we already know. But we have already colored the edges of KT, these T vertices at the other end of those blue edges. They're all connected with edges, and we've already colored them. So we're guaranteed one or the other of two. And we've got to make sure that in either case, we're good. So among the T vertices, we either have a blue Kn minus 1 or a red Km. If we have a red Km, well, we're good already. We are already good because we were looking for a red Km. And if among those T vertices there is a red Km, well, then we are happy. Good. We go home. But what if there is a blue Km? What about if there was a blue Kn minus 1, not Kn, Kn minus 1? Because we didn't really want to, well, Kn minus 1 is good and dandy, but we want a blue Kn. We want more than the blue Kn minus 1. Now we remember about V, but V is connected to every one of those vertices with a blue edge. That's how we came up with those T vertices. So together with V, all of those vertices are connected, these n-1 vertices with blue edges, and V is connected to all of them with blue edges. So together they make a blue Kn, and we're good. We have our wish list. We either have a red Km or a blue Kn. Okay, now the other case is going to be almost identical. So again, what we have colored the edges of K. I'm just repeating myself over and over again. You should maybe stop the video at this point and try to do this case yourself. Edges of Ks are colored blue and red. We want a blue Kn or a red Km. That's our wish list. This time I'm going to call L to be the Ramsey number n comma m minus 1. And we are in the case where I know that at least L of the edges incident with V are red. V was that one vertex that we are focusing on, and I know that L of the edges coming out of it are red, and L is this Ramsey number. So again, I consider the L vertices at the end of these red edges, and I know that L is a Ramsey number, so that's telling me something. It's telling me that KL arrows to a blue Kn or a red Kn minus 1. So what does that mean? That means among those the L vertices, which were at the other end of the red edges incident with V, among those, either you have a blue Kn or a red Kn minus 1. Again, in one case, if I have a blue Kn, well, I'm happy already, because that was one of the things I was looking for, a blue Kn, a Kn with all the edges among them blue. But what if I have a red Kn minus 1? And again, this time, together with V, because V is connected to those m minus 1 vertices, in fact, to all those L vertices with a red edge, but in particular to those m minus 1 vertices among those L vertices, but by a red edge. And so all those edges are red. The ones among those L vertices, m minus 1 vertices are red. And then this one coming out of V, all the edges coming out of V are red. And so we get a red Km, and we are done. So just to recap, what we have shown is that if you have two positive integers, then you can pick your positive integers, 47 and 94. Then Ramsey's theorem doesn't tell you how big S is, but it says that there is a large enough S, might be very large, such that Ks arrows to a blue K47 or a red K94. So there's some S, and if you find that S, then if you take a complete graph with that many vertices and color all the edges blue and red, then your wishes come true. And what's your wish? Your wish is to have a blue K47 or a red K94. And one or the other one of those, or both, maybe more things, but at least one of those things will happen. And in fact, we proved more than that. We've proved bounds on the Ramsey numbers. These are not necessarily the best bounds we can come up. They're better general bounds than these even. But this give us some kind of a bound on how big this number can be. And again, I hinted that just this proof gives us a binomial coefficient bound for Ramsey numbers, which we'll pursue later. This was the end of this lecture. I will see you in the other lectures on combinatorics. There is a link at the description of video that sends you to an annotated list of all the videos for combinatorics.